Hello everyone. For the past couple weeks we've been working with three-dimensional figures. We're going to continue with that. But the last 2 weeks we've worked with different types of polyhedrons and then how those polyhedrons would translate if they were given circular measures. Now we're doing one where it is definitely not a polyhedron. Today we're going to talk about a sphere. Now a sphere is a three-dimensional figure that is formed by the set of all points equidistant from a single point. That's very similar to a definition that we had before, the set of all points equidistant from a single point that are in the same plane. That's for a circle. But remember when we first defined circles, you guys gave me the definition of a sphere, and I said, no, it has to be in the same plane. Or one of you said that it has to be in the same plane. But if we want to draw a sphere, it's kind of hard to do. You would need either shading, or here's how I do it. I draw a circle, and then I draw a dashed ellipse on the circle that gives it the illusion of depth. That we've got that circle going around and this circle here as the outline. And we've got our center and that. So this point is our center. That's the center of the circle. And the distance from the center to any point on the circle is our radius. So that's all the same terminology as we've had from circles. It's the same terms for a sphere. And if you have a segment that has one point on the circle, has both endpoints on the circle and passes through the center, that'd be a diameter of the sphere as well. We don't really use the diameter of the sphere, so that's why I'm not going to even draw it in. Now this circle here, this dashed circle, and even this big circle here, if there is a circle on the sphere that has the same radius as the sphere, that's called a great circle. Oops. There are an infinite number of great circles on a sphere. Every circle you could draw on the sphere with the same radius as the sphere is a great circle. But that's not all the circles that we can have. I could draw a little circle up top here, just like taking a slice, taking a knife and cutting through the circle, through the sphere, and that will create another circle. A circle that does not have the same radius as the sphere is going to have a smaller radius. So since it's smaller, these are called lesser circles. There are an infinite number of great circles. There's an infinite number of lesser circles. We're not going to do much with the lesser circles, but they do exist. And one of the ways that these are used most is with cartography. I'm going to talk about that in a later video. So these are the critical parts of a sphere. We've got the center, we've got the radius, and most importantly, we've got great circles that are circles with the same radius as the sphere. All right. So let's talk about surface area of a sphere. The easiest way to figure out the surface area of a sphere is to think about a baseball. So I've got a sketch of a baseball here. It's a sphere, and the exterior of the sphere, it's two strips of leather stitched together by seams. So if you were just looking at the front of the baseball, it would look like this. If you had like a two-seam fastball coming at you, you'd see that. And then the side, it's like this. So it's really two strips of leather. And they fold into each other and wrap around the sphere. They're the same size, And yeah, I know it's not exact, but... So, what would happen is this would tuck into here. This would end up wrapping around until this tucks into there. This curve tucks into there. And this part that you don't see would tuck back into here. And that would cover the whole sphere. Well, these strips of leather, essentially, it's like a circle there, a circle there, a circle there, and a circle there. All 4 of these circles would have the same radius. So all 4 of those circles would have the same radius. But then there's this strip of leather in between. Now, this piece here, the edge of that would be like these sides. So this would be the radius of that circle on the strip of leather, but that's not the radius of the sphere. The radius of the sphere is a little bit more. So the radius of the sphere is a little bit more than the radius on the strip of leather. Now, if you were to make up that difference, if you were to take this green section here and distribute the area here around that, just make a concentric circle around this circle, it actually balances out to give you the same radius as the sphere. So this circle with the additional green area from here would give you the same radius as the radius of the sphere. And you would take this half of the leather connection and distribute around, this half the leather connection, distribute around, this half the leather connection, distributed around. So we end up with 4 circles with the same radius as the sphere. So that gives us our surface area formula for a sphere. The surface area for a sphere is 4 times the area of a great circle, 4 pi r squared. All right? And then for the volume of a sphere, we're actually not going to derive the volume formula here. The best and easiest way to derive the volume formula of a sphere is using calculus. Once you learn integration, the derivation for the volume formula of a sphere is very, very easy. So we're not going to do one of those complex non-calculus derivations just because you guys will be able to derive it in just a few years. And that in the grand scheme of things, it's not really a long time to wait. So here's the volume formula of a sphere. Oops. It's 4/3 pi r and r cubed. All right. A very important thing to remember is it's cubed for the sphere's volume and squared for the sphere's surface area. Just remember volume is units cubed, so that's why that's cubed. You need 3 dimensions, and all the dimensions are the radius. For surface area, it's area, so you need 2 dimensions, so that's why it's squared. All right, so those are the values of a sphere. Have fun.